this lesson, I'm going to talk about the analysis of linkages. And there are really three parts that we can focus on. The first part being motion or position of the linkages in space. The second part being velocity of the linkages. And the third part being acceleration of the linkages. And what we want to do is we want to make sure that we can analyze these linkages so that we can do things such as cycle time. So velocity gives us the ability to do cycle time. We can look at internal forces. We can do that through acceleration. And then we can just look to make sure that physical linkages do not interfere with other physical linkages. So with this in mind, what we're going to talk about is motion. And for this, these planar mechanisms, again, remember we're looking at planar mechanisms. We're going to look at translation in the x and y and then rotation in the z. So if I have a planar mechanism, just a single link attached to a ground joint, a point here can move in the x, move in the y, and also rotate in the z. So my coordinate system is configured something like this, right? So we can talk about this complex motion. In order for us to understand this complex motion, well, we can represent linkages as vectors. Okay, so I will draw a linkage here. Okay. So that's a linkage, and just like in Despicable Me, vectors have both a magnitude and a direction. So we've got this line here that represents a link. Its magnitude is r, so that's the length of that line. And its direction, in this case, is theta. Okay? And this theta is measured from this x-axis counterclockwise. Okay? So we can represent all mechanisms or linkages as vectors. So let me just take a quick pause here. We're going to come back to this, but let's draw a 4-bar mechanism. So if you're following along, I sketched down a 4-bar mechanism on here. Okay. So this is our 4-bar mechanism in reality. Looks something like this. Now we can take this and create a kinematic diagram of it. So a kinematic diagram will look something like the following. 1, 2, 3, 4 links, A, B, C, D, okay? And 4 joints. And we can represent it as vectors, okay? And there's not going to be a big difference between the kinematic diagram and the vectors. We've got vector 2, vector 3, vector 1, and vector 4. Okay, so these are our vectors, and each of these links is translated into a vector, and these vectors all have both a magnitude and a direction. I'll come to these in the next few slides. So all of these have a magnitude and a direction. In the next slide, we're going to introduce you to this example of a vector loop. And simply put, vector loop is the following. if I were to start a journey right here, so here I am, my little stick figure. If I were to start a journey right here and walk this way, okay, I would end up back at the same spot. Okay, so I'm going to make a loop, and I'm going to walk along these vectors. When I do that, I'm going to make a loop. My net displacement is what? Okay, think about this. Scratch this down. And the answer is 0. My net displacement is 0. Okay? Now, in order to get to this net displacement, I walked along these vectors. So actually, I walked along L2, and L2 is going in the same direction as me. I walked along L3, and L3 is going in the same direction as me. I'm in the opposite direction of L4, and in this case I'm in the opposite direction of L1. And all those things equal my net displacement. Okay? So this is what we call a vector loop. So just what I said, it's for closed linkages. Okay, so a vector loop is for closed linkages. And the equations that I give you at the end of this are going to be solved for closed linkages. Now in actuality, we can do this for open linkages. So if I have a system that looks something like this, and I want to know where this point x is, I can represent this as vectors. Okay? And x, y coordinate system. So I can represent this as vectors. Alright, so let's dive a little bit further into vector loop. So vector loop, we talked about it before. This is important. This is the notation that we're looking at. Everything after here is going to be solved for this type of notation.